Okay, so now this hour we'll do inverse trigonometric functions, but let me finish what we started last hour about E, the number E. Okay, so E as a limit. So this is very ubiquitous. It shows up a lot of the time. So let us look at this. So we want to show here, okay, so we will show that E is equal to limit as h goes to 0 from the right, 1 plus h to the power 1 over h. Okay, so later on we'll see a quick way of proving this using L'Hopital's rule, because you see this is an indeterminate form. Two forces are fighting against each other. Inside, the limit is 1, okay, and 1, anything to the power 1 should be 1, but the power is going to infinity, so the power claims anything to a very large power is either 0 or infinite, okay, depending if it is larger than 1. Since inside is always larger than 1, and the power goes to infinity, this says let's go to infinity. Okay, so one of them is pulling this down to 1, the other one is pulling down to infinity. So this is a typical setup for L'Hopital's rule, which we'll do maybe on Friday. And we're applying L'Hopital's rule here. We'll find that the limit is E, but now there's an easy, tricky way of getting the limit as E without using L'Hopital's rule. So that's what we will do. So we start with f of x equals ln x. Okay, and we know that f prime x is equal to 1 over x. Okay, we also know here that f of 1 is 0, and here we know that f of f prime 1 is 1. Okay, so now the trick is we want to write this using the definition of derivative. Okay, so 1 is equal to f prime 1. Okay, so this is limit as h goes to 0. Well, it has to be from the right because f of x is always taking positive values. Okay, so this is f of x plus h minus f of x. Here x is 1. Okay, so let me do that. So I'm taking derivative at 1, so 1 plus h and f1 over h. Okay, so let's see what happens now. Now next, limit h goes to 0. F of 1 plus h from definition is ln 1 plus h. F of 1 is 0, okay, divided by h. Okay, so now, you know, if you call this a trick, this is the trick. Instead of looking at this, I realize that this is ln 1 plus h times a constant. So the rules of logarithm tells me that this is h goes to 0 ln 1 plus h to the power 1 over h. Okay. Okay, now we can exaggerate. Now that you caught this, you can play it as a cat playing with the mouse. So logarithm is continuous, so it comes out ln of limit h goes to 0, 1 plus h, 1 over h. So you see this is precisely what we want to calculate on this side. And I know that its logarithm is equal to 1, taking exponential of both sides. So taking these here, we know that E is equal to limit h goes to 0 from the right of 1 plus h, 1 over h. Okay, so let me make this clear. This is h. Okay, so this thing is generally not used in this form, but instead of h, you want to put an integer. Okay, so that's generally how it shows up in calculations, and that's how you use it. Okay. So in practice, we put h equals 1 over n for positive integers n. Okay, so then e is equal to limit as n goes to infinity. Okay, since h is going to 0 from the right, and the integer n must go to infinity, 1 plus 1 over n to the power n. Okay, so this is how we use this. So later on we'll see that if instead of 1 you put x, you get e to the x. Okay, so we'll do that. We'll do that later. Okay, so but this thing, this you can use this part to approximate e, but the approximation is very small. It's very slow. Okay, so this can be used to approximate e, but the convergence is extremely small, extremely slow. Okay. So what did I get here? So for example, let's check this thing. 1 plus 1 over n. Okay, so for example, if you put n equals 1, you get 2, which is not good. Let me write the first few things. 2.27. Okay, so we know that e is 2.7, 1828, and then something else. Okay, so 2.37. Okay, so it's increasing but very slow. 4 is 2.44. Since we have computers, you start giving larger and larger numbers. When you give 1 million, then you get 2.718804. Okay, so at least you get this much conversion, this much correct. Okay, but the others are, you see, this is still very small here. This increases. So that's another problem. You can play with these things. You can show that it's an increasing function because you observe that it is increasing here. So it is really increasing. In between, maybe it goes down or up. It doesn't. Okay. Okay. Let's do one more thing, which shows up again. So let's take the following function and let's look at its derivative. Now that we can take any number to any power, the question is, how does x to the power x behave? Okay, so now consider the graph, the function f of x equals x to the x. Now the base must be positive, so the domain of this is positive real numbers. So what is its graph? Mean, well, does it have a mean? Does it have a max? Its limits, etc. Okay, so first we have to look at the derivative. Okay, so f of x equals x to the power x is equal to e to the power x ln x. Okay, so now I know how to take derivatives. Okay, so f prime x is equal to derivative of exponential is itself. So first of all, I have x to the power x. Now I multiply with the derivative of this. So maybe just to remind ourselves what we are doing, let me do it this way. So this is x to the x, 1 times ln x plus x times derivative of ln x is 1 over x. They cancel and you get 1. Okay. So you see, this is always positive. So the sign will be determined by this. Okay, so the sign of f prime is determined by this factor. Okay, so first of all, when is ln x plus 1 equals 0? That is ln x equals minus 1. We know that, well, we take exponential of both sides. This is 1 over e. Okay. ln is an increasing function. Its derivative is 1 over x, always positive. Okay. So if it hits 0 at this point, or rather if it hits this value at this point, before this point it is below this, and above after this it is larger than 1 over larger than minus 1. Okay. So ln x plus 1 is positive for x larger than 1 over e, and negative for x less than 1 over e, and 0 when x is equal to 1 over e. Okay, so this tells us that at this point there is a minimum, okay, because the function is decreasing when x is between 0 and 1 over e. This is between 0 and 1 over e, because this is not defined when x is 0 or negative. So the function is decreasing. It decreases up to the point when x equals 1 over e, and then it increases. Okay. It goes to infinity. When x is very large, it goes to infinity. So what happens when x goes to 0? So that we will see on Friday. Okay, so limit as x goes to infinity of x to the x is equal to, okay, let's look at this part, limit x goes to infinity e to the x ln x. So this goes to infinity, this goes to infinity, so this is e to the infinite. But limit as x goes to 0 from the right of x to the x is limit x goes to 0 from the right e to the x ln x. So this is going to be e to the limit x goes to 0 from the right x ln x. Okay, so we will see on Friday when we do L'Hopital's rule that this limit is 0. Okay, so that's going to be a general rule. If a polynomial fights against a logarithm, polynomial wins. We will show this by L'Hopital's, but at this point let's just take it for granted. Okay, so ln x wants to go to minus infinity, this wants to go to 0. Nobody listens to ln x. Remember how small the graph increases or decreases. Okay, so this is equal to e to the 0 equals 1. Okay, so the graph is then, so this part we'll do on Friday. Okay? So we'll do this limit later. So there we use L'Hopital's rule. Okay, so just let's borrow this, then the graph looks like this thing. X, y. So it starts from 1. Okay, so if that is 1, then this is also 1. Somewhere here we have 1 over e. So the function, when you put x equals 1 over e, you have 1 over e to the power 1 over e. Did I calculate this? I didn't. Apparently, I calculated 0.69, so it is somewhere here, 0.69. So the function is like this. Okay, so this is the graph of y equals x to the x. Okay. So let's now pass to inverse trigonometric functions. Remember that our aim in doing these things is to find new formulas for integration. Okay. Trigonometric Okay, so we can we do these things using the same idea we mentioned last hour for inverse functions. We use y equals f of x if and only if x equals f inverse y, or whichever way you want to write it. Or maybe, since we are interested in inverse functions, so let me put the inverse here. Okay, so I understand f. I'm trying to understand f inverse. Since there is this relation, in particular, I'm interested in the derivatives. I don't know how to take the derivative of y here, okay, because I don't understand this function. I only know that it is inverse. So I go here. Here I take the derivative of y with respect to x. So here I use chain rule. Okay. So here I want dy dx. Okay. So I calculate it here. Okay. So d dx on this side is equal to d dx on this side. Okay. Derivative of x with respect to x is 1. Here, derivative of this using chain rule, this is f prime y times y prime. Okay, so this is, you see, this is y prime. Now, this is true for every inverse function. So the derivative of the inverse function is equal to 1 over f prime y. Okay. The crucial part here is I want to express this in terms of x. Okay. Now we want to express this in terms of x. Okay. So theoretically it's possible, but practically you want to actually put the value here. Okay, so somehow you have to put this y is equal to f inverse x, and then you evaluate f prime at that point. Okay, so you don't know how to do these things in general, but with trigonometric functions, using trigonometric identities, there's a nice way of doing these things. Okay, so that's why we look at inverse trigonometric functions. We are also skipping a page from the book, skipping a section, hyperbolic functions. Hyperbolic functions are also good in this sense. You can write the inverses. Okay, but let us now apply this to trigonometric functions. Okay, so we want to apply this observation to some common trigonometric functions. Okay, so let's do this. So first we do this for sine function. Okay, so first sine inverse x is equal to y. Okay, so this is, sometimes we write this as arc sine x equals y. This is the same thing as saying that x is equal to sine y. Okay. Always remember that we are playing this game in this section to derive integration formulas. So we have to know some derivative formulas, and their inverses with respect to integration will give us new formulas. Now we take the derivative. Okay, so as we did here, 1 is equal to cosine y times y prime. Okay, so I don't have to erase this, times y prime. Okay, so y prime is equal to 1 over cosine y. Okay, so how do I write cosine y in terms of x? I know sine y. Okay, so here I have sine square y plus cosine square y is equal to 1. Okay, sine is x, so this is x squared plus cosine square y is equal to 1. I am interested in cosine y, so this is 1 minus x square. Cosine y is equal to 1 minus x square. We'll decide on the sign of this plus or minus, so at this point let us take it just like that. Okay. Then this one becomes, okay, so we'll draw the graph and see. Okay, so let's say plus or minus equals 1 over plus or minus square root 1 minus x square. Okay. Next domain. Okay, so it is clear that here x cannot be very large, but then we check that x is sine y, so x can be plus 1, minus 1, and that's the maximum. And it's not going to take those values because in that case the derivative becomes infinite, so apparently there is some vertical tangents there. All other values of x are less than, in absolute value, less than 1, which is which is okay here. So this is x less than 1. Okay, so algebra carries us up to here. So this is the derivative of arc sine. Let us now look at the graph and decide on those signs. Okay, so to decide on the signs, so let us look at the graph. I don't know, of course, this function yet, but the graph of this thing is going to be the mirror symmetric or symmetry of the graph of sine x across the mirror y equals x. Okay, so that's what I will do now. X, y. Okay, so sine x is periodic. Okay, you cannot take the inverse image of a periodic function because it takes the same value infinitely many times. So you have to decide to choose a particular natural looking period of the function and invert that. So for sine, what we take is the following. This is minus pi. This is, okay, so let me draw this and then, so it goes like this. So this is pi. So this part is 1, this part is minus 1. So this is y equals sine x. Now I consider the mirror. So here my graph is not convincing, but okay, so the graph is something. This is y equals x. Okay, so we know that here the tangent is 1. Mm-hmm. Pi over 2, right. Sometimes you say these things after class, then it is meaningless. Okay, so now you got credit for seeing this. So I say to the camera that class is not sleeping. I'm not the only person who's awake here. Okay, now we reflect this on this side and see what happens. You see, when you reflect this part becomes here, and since this is horizontal here, it becomes vertical. So let me draw it here. X, y. Okay, so here I have minus 1. Here I have 1. Okay, so this part will become pi over 2, and here I have minus pi over 2. Okay, so when I reflect it over here, you see it will be horizontal, perpendicular. It will be like this. And here it's also the tangents at these points are perpendicular. So if I calculate this algebraically, I expect 1 over 0 there. Well, that's what happens here. So this is y equals arc sine x. Okay. It is always increasing. Okay, so this is increasing. When you flip it over, it is again increasing. Always increasing. So y prime must be positive. Okay, positive or, well, positive. Hence, y prime is equal to 1 over plus square root 1 minus x square, and x is between. So here y equals arc sine x. Okay, so with a little bit combination of algebra and geometry, we totally understand this. We can also do the same thing for cosine, but before you do calculation, you should always stop and think for a few seconds to decide what you expect. We don't expect a different formula. We expect a similar looking formula because this formula was derived from this equation. I solve for this. If I do this for arc cosine, I'll solve for this, okay? Because derivative of this is here and I solve for it. Derivative of this is here and I solve for it. So I'll have the same thing, y prime, when if y is arc cosine, I'll have y prime 1 over plus or minus the same expression. So it will not increase my knowledge about my antiderivatives, but we can do it just for fun to see how it works. The crucial thing here is again to find a part of the graph of cosine x to invert. Again, cosine x is periodic. Okay, it takes the same value infinitely many times. We want to find an interval where it is 1 to 1. Okay, so let's do that quickly because we don't expect a new formula. We already guess here correctly that the derivative will be plus or minus this thing. So let's just find a period of cosine to invert. Okay, to cosine inverse x equals y if and only if x is equal to cosine y. Okay, so sometimes we write this as arc cosine x equals y. So here the main part is to find a period of cosine to invert. Okay, so we know that cosine. So we start from here. If you go like this, okay, so now if you increase this, you'll take the same value twice. So this is y equal cosine x. This is 1. So this is pi over 2. This is pi. Okay, so we want to see the reflection of this. So you see, if I reflect this around here, this point is going to come here. So it will be something like this. Okay, at the end point, since these are horizontal here, okay, so the derivative here is 0. When I reflect it here, it will be perpendicular. So it again agrees with this formula. At the end points, I get 1 over 0. And since when I reflect here, the graph will be something like this. It is always decreasing. So I'll use the minus sign. Okay, so let's now reflect this. So it will be something like this. So this is now 1. This is minus 1 x y. This is pi over 2. This is pi. Okay, so this is now y equals arc cosine x, always decreasing. So y prime must be negative. So we know from these arguments that y prime will be exactly the same formula. So y prime is equal to minus 1 over 1 minus x squared. Since I will start doing exactly the same calculation, but instead of solving for cosine, I'll solve for sine. Okay, so this is d dx arc cosine x. Okay, so this didn't give us anything new, but derivative of arc cosine gave us something new. Okay, so let's see if we can do this for tangent. Okay, so tangent also gives us something nice. So let's do this with tangent. Well, with secant sometimes. Okay, let's do this with tangent, see what it amounts to. Okay, so y equals arctangent x. So this is, you see, tangent inverse x. But we generally don't use this, it's confusing. So this is true if and only if x is equal to tangent y. I'm interested in y prime in these things. We are trying to find derivative formulas. So here one is derivative of tangent is secant square y times y prime. Okay, so y prime is equal to 1 over secant square y. So I have to find a relation between secant and tangent. Okay, I want to be able to express secant in terms of tangent, and tangent is x. So I will be able to give a formula for there. So what formula do we know between relating tangent to secant? Okay, if you take the square of one and square of the other, do plus or minus, you should get 1 somehow. So which one? Okay, which one? Okay, let's try 1 plus tangent square. Tangent square is sine square over cosine square. If you add 1, you get sine square cosine square in the numerator. That's 1. 1 over cosine square, secant square. Okay, so we have 1 plus tangent square x, or let's say use y here. Y is equal to secant square y. Well, it's already there. It's very convenient. So I take this over here. This is 1 over 1 plus tangent square y. And tangent is x. Now I take it over here. 1 over 1 plus x squared. Okay, now this is totally new formula. Okay, so this gives derivative with respect to x of arctangent x is equal to 1 over 1 plus x squared. So we knew how to integrate if we had x here, x over 1 plus x squared, then this x dx is actually the differential of this. So the antiderivative of that would be ln 1 plus x squared up to some constants. Okay? But if we didn't have x here, if we just have 1, we didn't know how to find the antiderivative. But now we know the antiderivative. Okay, so I'll leave the graph of this for you to look in the book. Let me do quickly secant. Okay, so secant gives a new formula. That's why we do it. But there is no, so these parts, you want to integrate, you want to look at the graph of this. There's an obvious part for the arctangent. But when it comes to secant, there is no easy way. Well, so everybody chooses a different way. So let's look at arcsecant. Arcsecant. So this is generally arcsec or whatever. Arcsec. X equals y equals x equals secant y. So let us look at secant y. First of all, we look at cosine x. So you see this is cosine x. X, y, this is y equals cosine x. Now I want to look at y equals 1 over cosine x, which is secant x. So at these points, this is what? Minus pi over 2, pi over 2, and this is, well, this is 3 pi over 2. Okay, so at those points, the function will be infinite, right? This is 1, so here I have 1, and this is minus 1, so here I have, let's say, minus 1, plus 1. Okay, so here the function will be something like this, and here the function will be something like this. Okay, so we have to find, we have to choose sections to invert. So what we do is, okay, you have to choose one arm here. You see this one is not invertible. So you can choose this one, and then here you choose this one or this one. So the book does the other way around. I'll just show you that you can do this one. So here, this one, up to here. So we choose to invert these parts. Okay, so this is pi. So this is pi, and this is 0. Okay. So we decide that x equals secant y. When I choose y, okay, now I change. I'm here now. Now I come here. Y is between 0 and pi over 2. So I'm taking this branch. Y is between 0 and pi over 2, but pi over 2 is not included because it's infinite there. And then I pass to the other branch. Pi over 2 is minus infinite, so it's excluded, and I go up to pi. That pi is included. Okay, so we decide to take the inverse function like this. The advantage is that when I take the derivative, I will take the positive sign because you see in this interval the function is increasing and the function is increasing. So I don't have to consider different signs. Okay, so here again, taking derivative 1, so taking derivatives 1 is equal to, what is derivative of secant? What's derivative of secant? Anybody awake? Huh? Anybody awake? What's the derivative of secant? Huh? Secant x, secant y, tangent y. Huh? Is this the formula? Kare öbüründe olacaktı ya. Huh? So those who are awake agree. Those who are sleeping, they don't care. So let's continue. And we need, by chain rule, we have to take y prime. So y prime derivative of arcsecant x is equal to 1 over secant y times tangent y. Secant y is easy. That's already x. Okay. So this is equal to 1 over x times tangent y. And this tangent y we take from the other. 1 plus tangent square y is equal to secant square y. So this is equal to x square. So tangent y is plus or minus square root x square minus 1. Okay. So I'll have here 1 over plus or minus x square minus 1 square root. Okay. But from the figure, from our choice, we chose that branch of the inverse so that the function is always increasing. Okay. And the domain, in the domain this is always positive. Okay, so the function is always increasing. So we take plus sign. Okay, so we found that derivative respect to x is arcsecant x is equal to 1 over x x squared minus 1. Okay, so here you see x is here. I'm taking, this is the function itself. This is the second. When I take the inverse, I have to look at the, okay, so I didn't look at that one. So this thing will be here. Okay, so this thing will come here and it will be increasing. Okay, so let's just do that last part here. Okay, so this thing will come here. It will be somewhere here. It will be increasing. And this thing will be over here. Well, I didn't see where it will be. Okay, so it will be, you see this thing will be over here, so it will be up over there. Okay, so I'll just show you this part. So this is increasing. Okay, so maybe check this part, check this as a homework, check this comment on the figure after you reflect the graph of y equals secant x. Okay, so you reflect this and then check if it is increasing or decreasing. Because then you can say, you may decide that for some values on this part, you see on this part, x is, you will take the positive sign. On this side, now I couldn't see where this goes. Okay, so maybe on this side the inverse function is decreasing, but I'm not sure. It must be increasing. Okay, so I'll stop here. So this one. Okay, so in this part, generally, arcsecant comes with complicated things, but in the general development of the theory, we will need this one. Okay, so because these formulas will be used when you want to take the integral of a rational function, a polynomial over a polynomial, assuming that you know all the roots of these things. Okay, then you split these polynomials, and then the antiderivative becomes a combination of logarithm, arctangent, and polynomials. Okay, so that's all for today. But before you go, you have to fill out this surprise quiz that Abdullah Hoca has sent to you. Okay.